Welcome back to Cosmic Sedation, your safe haven for cosmic dreams. Tonight, we explore a fascinating idea. What if black holes are doorways? These enigmatic regions might just be passages to other realms or times. If you enjoy our journey through the cosmos, hit that subscribe and like button, won't you? Drop a comment letting us know where you're listening from tonight and what time you usually drift off. And now, let's gently begin our cosmic sojourn together. At the event horizon of a black hole, time dilates to such an extent that for an outside observer, matter seems to take an eternity to cross this boundary. Yet from the perspective of the falling object itself, its journey toward the singularity happens in an instant. This paradox is one of the most confounding aspects of black holes. Imagine a spacecraft floating just beyond the event horizon of a supermassive black hole like that at the center of Galaxy M87. The ship's instruments show temperatures near absolute zero, around -230 degrees Celsius, but no freezing occurs because time dilation prevents any real cooling process. From our perspective on Earth, it would take countless years for the ship to cross this final barrier. Yet from inside the spacecraft, the crew might experience the descent in mere seconds before reaching an end point where space-time bends so severely that even light cannot escape. Once past the event horizon, matter spirals inward toward the singularity under immense tidal forces. For a black hole with 1.4 solar masses, its Schwarzschild radius measures just 8 kilometers, smaller than many cities on Earth. This object contains more mass than our Sun compressed into an area smaller than Manhattan. As matter stretches infinitely during this descent, it elongates in one direction while being squeezed in others, creating a process of infinite stretching. The pressure and density become so intense that time itself slows down until it almost stands still. Inside the event horizon, space-time bends so severely that even light cannot escape. In a region known as the photon sphere, photons orbit at the boundary of escape velocity. Beyond this point, any attempt to reverse course is futile. For objects like our hypothetical spacecraft, tidal forces tear apart their vessel and bodies. This process takes place over mere seconds from their viewpoint, but could last millions of years as seen by someone far away. Astronomers have observed that black holes grow by accreting matter, with smaller ones growing faster than larger supermassive counterparts due to higher relative accretion rates. For a typical stellar black hole, this accreted material forms an accretion disk around the event horizon, heated to millions of degrees Celsius through friction and magnetic fields. The temperature near its surface reaches 1 femtokelvin, astonishingly close to absolute zero, yet paradoxically hot enough for some quantum effects like Hawking radiation to occur. As matter stretches infinitely toward the singularity within a black hole, it passes through regions where time loses all meaning and physical laws break down. In these extreme conditions, even familiar concepts of space and time dissolve into something unrecognizable. For humans, such an encounter would be unimaginable, both in scale and experience. Yet this process continues ceaselessly across the universe, shaping galaxies, influencing star formation, and possibly serving as gateways to realms beyond our comprehension. These cosmic phenomena are not just distant curiosities, but integral parts of the universe's ongoing evolution. They have been growing since the early epochs of the cosmos, some even predating the oldest stars in our galaxy. The iron in your blood was forged in a star that died before our sun existed, and it may eventually find its way into a black hole. This process of matter cycling through cosmic events is a reminder of the interconnectedness of all things in the universe. As we observe these phenomena, we are witnessing not just distant curiosities, but integral parts of the universe's ongoing evolution. A proton, a fundamental building block of atoms, is approximately 1 femtometer in diameter, far smaller than even the most powerful microscope can resolve. Yet inside the supermassive black hole at the heart of Galaxy NGC 4261, light takes roughly 13 billion years to traverse from its event horizon to the singularity. To put this into perspective, the distance light travels within that black hole is more than 1 million times greater than the span of all human history. Imagine a photon entering the event horizon of this supermassive black hole. Its journey through the inky depths towards the singularity would be akin to covering a distance equivalent to traveling from Earth to beyond the edge of the observable universe, multiple times over. In contrast, the proton within an atom on your hand is so tiny that it could fit into the event horizon of this black hole more than 10 trillion times without filling it. As light spirals inwards, it encounters layers of accretion disks and jets, complex structures formed from matter falling towards the singularity. The temperature near the event horizon of NGC 4261's supermassive black hole is estimated to be around -230 degrees Celsius. This might seem cold compared to everyday temperatures on Earth, but in the context of a supermassive black hole, this temperature is extraordinarily high. The irony lies in the fact that as matter approaches closer and closer to the singularity, it experiences an environment that, despite its extreme gravitational pull, remains relatively warm until very near the point where time ceases. This warmth is due to friction from infalling material and radiation. Consider now the lifespan of our universe compared to the journey of light within this black hole. 13 billion years have elapsed since the Big Bang. Yet inside NGC 4261's central supermassive black hole, light undergoes a trajectory equivalent to trillions upon trillions of cosmic ages before it can reach the singularity. This vast timescale underscores the incomprehensible nature of black holes as cosmic time machines, where moments stretch and contract beyond our familiar notions. The rate at which this light travels slows dramatically as it nears the event horizon due to intense gravitational forces. In this environment of extreme gravitational fields and near-infinite light paths, even the concept of scale becomes distorted. For example, the distance that light must travel from the event horizon to reach the singularity is so vast that it would take over 1 trillion years for light to cover just 1% of this journey at its current speed inside the black hole. A human body falling into such a supermassive black hole would experience an intense tidal force that stretches it like taffy, a process known as spaghettification, before reaching the singularity where both time and space cease to exist. Yet, for a brief moment, the traveler might be privy to one of nature's most profound paradoxes, witnessing their own end unfold across unimaginable cosmic timelines. The iron in your blood was forged in stars that died before our sun even existed. As light approaches the singularity, it encounters regions where quantum effects become significant, leading to phenomena like Hawking radiation. This process is incredibly slow for large black holes, but represents a subtle leakage of energy from the black hole's event horizon. The paradox here is that while the outside observer sees an eternal struggle for light to escape, inside the black hole, time and space are so warped that this journey ends abruptly at the singularity. Let us consider the peculiar nature of time near the event horizon of a black hole with 10 solar masses. Just outside this boundary, where gravity's pull is intense but not yet absolute, you would find yourself in a region known as the photon sphere. Here, light itself orbits the black hole in a series of complex paths, unable to escape its gravitational embrace. Time dilation becomes pronounced. Each second that passes for you stretches into an eternity for distant observers. This effect is due to the extreme curvature of spacetime caused by the black hole's mass, which bends time as well as space. For those watching from afar, your clock appears to slow down exponentially until it seems to stop entirely at the event horizon. The temperature near this region is extraordinarily cold, around 1 femtokelvin, a record low even in the vastness of deep space. This frigid environment is devoid of particle collisions, which typically create warmth through kinetic energy exchanges. Yet, paradoxically, closer to the event horizon, where matter falls toward the black hole with increasing speed, temperatures spike due to friction and radiation emitted from accretion disks. These hotspots contrast sharply with the near-absolute zero experienced in the photon sphere. Imagine now what it would be like for you to witness the passage of time from this unique vantage point. To someone far away, your every action, each breath, each heartbeat would occur at an excruciatingly slow pace. Years might pass before they see even a moment's worth of activity. This is not just theoretical. It has practical implications for communication and observation. Any signal sent from near the event horizon would take an immensely long time to reach distant observers, creating what appears to be a delayed or frozen image of your existence. The black hole you are near has been accumulating mass for billions of years through accretion, capturing matter from nearby stars and gas clouds. Its growth rate is inversely proportional to its size. Smaller black holes grow faster than larger ones like this one. This supermassive black hole may have formed shortly after the Big Bang, feeding on a diet of early stellar remnants and gas clouds. Over time, it has evolved into an entity that could outlast even the universe itself in terms of its longevity. As you hover near the event horizon, the fabric of spacetime around you is so distorted that light paths become convoluted and unpredictable. This phenomenon, known as gravitational lensing, can create multiple images of distant objects or distort them beyond recognition. For a moment, consider how this might affect your perception of the universe around you. The familiar constellations could appear fragmented or duplicated, their positions seemingly shifted due to the bending of light by the black hole's immense gravity. This warping effect not only distorts your view, but also challenges our understanding of distance and position in space. The environment near a black hole's event horizon is one where time itself becomes a fluid entity, its flow disrupted and stretched beyond recognition. The photons orbiting the black hole do so in a manner that defies conventional physics, creating an intricate dance of light and gravity. This region, known as the photon sphere, showcases the peculiarities of nature at extreme gravitational fields. Here, the laws we take for granted on Earth, such as the constant speed of light or the uniform passage of time, are bent and twisted into something far more complex and fascinating. Each orbit of a photon around the black hole represents a delicate balance between gravity's pull and the inherent properties of light itself. This delicate dance continues indefinitely, as long as the black hole remains intact, showcasing the enduring nature of these cosmic entities. At the edge of a black hole's accretion disk, particles perform an intricate dance, spiraling closer and closer to the point of no return. They loop around in an accelerating whirlwind, reaching speeds that are just shy of the speed of light. Each particle is caught in a gravitational tug-of-war, pulled by the immense mass at the center while resisting being swallowed forever. The innermost stable circular orbit acts as a boundary for these loops, beyond which no object can safely circle without being torn apart by the black hole's tidal forces. This ISCO marks a region where space itself is stretched to such an extent that even light struggles to maintain its path. For particles caught in this dance, their orbits are not fixed but dynamic, constantly adjusting as they approach the event horizon. Each loop around the accretion disk takes less time from the particle's perspective than it would for a distant observer. This phenomenon, known as gravitational time dilation, ensures that these loops accumulate at an ever-increasing rate. The closer to the black hole, the faster this process occurs, creating a frenzied whirl of particles caught in a cosmic merry-go-round. Astonishingly, if you could somehow observe from within this region, time would feel normal for you, even as each loop around the ISCO seems to take less and less time compared to an observer far away. These loops are not merely circular, but form complex patterns that weave through space in a manner akin to chaotic orbits. The paths of these particles are influenced by quantum effects near the event horizon, leading to fluctuations in their trajectories. While classically they might follow stable paths, quantum mechanics introduces unpredictability, causing some particles to occasionally stray closer to the black hole's grasp than expected. The fate of these particles is intertwined with the history and future of galaxies themselves. Iron, silicon, and other elements forged in ancient stellar explosions have found their way into this cosmic dance, destined to contribute to the black hole's mass or potentially be flung outwards in powerful jets. For instance, one iron atom might complete thousands of loops before being absorbed by the black hole, while another could escape at high velocity, contributing to galactic winds that enrich interstellar space with heavy elements essential for star formation and planetary systems. As these particles race around their loops, they generate powerful electromagnetic radiation, X-rays and gamma rays, that can be detected by telescopes on Earth. This radiation provides astronomers with crucial information about the black hole's activity and the processes occurring near its event horizon. The energy released in this region is so intense that it outshines entire galaxies in certain wavelengths, making accretion disk some of the brightest objects in the universe. Yet, for all their brilliance, these regions remain among the most mysterious places in space, challenging our understanding of physics and cosmology alike. Particles near the ISCO experience an unexpected phenomenon. They can emit bursts of energy that briefly resist the black hole's pull. These sudden emissions are thought to be caused by quantum fluctuations in the vacuum near the event horizon, creating temporary particles that interact with the accretion disk material before disappearing again. This process introduces a layer of complexity and unpredictability into an otherwise predictable system, hinting at deeper connections between gravity and quantum mechanics. The particles' journey ends abruptly when they cross the event horizon, marking a point where not even light can escape. Once inside, the particles are pulled into the black hole's singularity, where time ceases to have meaning and the laws of physics break down completely. This final act is a testament to the relentless pull of gravity and the ultimate fate of matter in extreme cosmic environments. Yet for now, as they dance at the edge, these loops remain a fascinating glimpse into the dynamic interplay between space, time, and matter in one of the most extreme places known in our universe. Imagine a dense cloud of gas and dust swirling around a supermassive black hole at the center of our galaxy. This cloud is known as an accretion disk, where gravity pulls material into a compact orbit. The disk's temperature can reach millions of degrees Celsius, causing it to emit X-rays that pierce through space. These high-energy emissions are not just intense heat, but also powerful forces shaping the birth and death cycles of stars. Incredibly, this process is akin to how water vapor condenses around a cold surface. The extreme gravity of a black hole causes gas clouds to clump together, sparking star formation across the galaxy. Yet from our vantage point on Earth, these X-rays are invisible, their energy too high for our eyes to perceive, and they reach us after traveling hundreds or thousands of light years. Each supermassive black hole at the center of a galaxy acts as a cosmic thermostat, regulating the temperature and density of surrounding gas clouds. If the black hole grows too large, it can heat up the nearby environment, preventing further star formation by dispersing gas particles. Conversely, smaller black holes accrete matter more quickly, generating energy that compresses neighboring clouds into new stars. This balance is delicate yet vital for sustaining galactic ecosystems over billions of years. Paradoxically, while these massive objects pull in material with immense force, they also play a role in releasing it back out into the cosmos through powerful jets and winds. These phenomena can travel at nearly the speed of light, carrying away gases that would otherwise condense into new stars. This dynamic interplay suggests that black holes are not just cosmic vacuum cleaners, but also architects of stellar birth and death. Consider NGC 4261, a galaxy where an immense black hole with 1 billion solar masses sits at its core. The accretion disk around this supermassive entity spans several light years in diameter, an area vast enough to contain thousands of stars. This disk is not just a passive observer, but an active participant in the life cycle of NGC 4261's stars. As gas spirals inward toward the black hole, friction heats it up to temperatures hotter than any known star, emitting powerful X-ray and gamma-ray radiation that can disrupt nearby clouds of stellar nurseries. This is a cosmic paradox. While black holes are often seen as destructive forces, they also indirectly foster new life through their influence on surrounding matter. The intense radiation from the accretion disk can ionize gas in adjacent regions, making it more likely to collapse into stars. At a distance of 100 million light-years away, galaxy NGC 4261 appears as a faint smudge through telescopes. Yet within this smudge lies an intricate ballet between the supermassive black hole and its accretion disk. The black hole's gravitational pull compresses gas into dense pockets that can eventually collapse under their own weight to form stars. This process occurs on cosmic timescales, with some star clusters taking millions of years to coalesce. Meanwhile, at the heart of this galaxy, material spirals toward the black hole in a complex dance governed by gravity and magnetic fields. The swirling patterns in the accretion disk are not random, but follow precise mathematical laws that have been playing out for billions of years since NGC 4261 first formed. This ancient cycle of birth and death, driven by the central black hole, ensures that new stars continue to emerge even as others burn through their fuel. The role of black holes in star formation extends beyond mere gravitational influence. They also dictate how galaxies evolve over time. In some cases, supermassive black holes can quench star formation entirely if they grow too large and energetic. This happens when the black hole's accretion disk becomes so luminous that it heats surrounding gas to millions of degrees, preventing further cooling needed for stars to form. Such an event can effectively turn off a galaxy's ability to birth new stars. Conversely, smaller galaxies with less massive central black holes tend to maintain active star formation longer. This dynamic interplay between black hole mass and galactic evolution is one reason why galaxies exhibit such diverse properties across the universe. Our own Milky Way, for instance, has an active but relatively modest supermassive black hole at its center, allowing it to continue forming new stars. However, recent studies suggest that even in galaxies like ours, where star formation remains robust, the central black hole can still subtly influence the distribution of elements within newly formed stars, potentially affecting their future evolution. Within the accretion disk of a supermassive black hole, magnetic fields play a crucial role in channeling material toward the central singularity. These magnetic forces not only shape the swirling patterns seen in simulations and observations, but also help regulate how gas spirals inward. As particles spiral closer to the event horizon, their paths become increasingly complex, looping around in an accelerating whirlwind that reaches speeds just shy of the speed of light. This intricate dance of particles is a testament to the delicate balance between gravitational pull and magnetic forces. The energy released from these interactions can be harnessed by surrounding stars, providing them with the necessary fuel for their formation and growth. Consider a moment just after the universe began, a fraction of a second when everything was extraordinarily dense and hot. In this primordial soup of matter and energy, regions with slightly more density than their surroundings could collapse under gravity's pull. These collapses gave birth to what we now call primordial black holes. They formed in conditions so extreme that quantum fluctuations played a crucial role, creating imbalances in mass distribution. These objects are thought to have appeared when the universe was mere fractions of a second old. They could be smaller than a city, but still contain more mass than the sun. Yet these black holes, if they exist, are incredibly elusive. Their presence would be inferred from gravitational effects on nearby stars or gas clouds, rather than direct observation. Their formation marks a unique moment in the universe's history, where quantum processes directly influenced gravity's pull on matter. Imagine the universe as an infant, still in its earliest stages of development. These primordial black holes could have been the seeds for cosmic structures like galaxies and clusters, sowing the first points around which matter began to coalesce. Their influence would stretch across light years, pulling on gas clouds with gravitational tendrils that spanned millions of kilometers. In a universe where space itself was rapidly expanding, these tiny seeds acted as anchors, eventually forming the massive superstructures we observe today. While most black holes are products of stellar death or mergers over cosmic timescales, primordial black holes offer a glimpse into the universe's earliest moments. Their potential role in seeding cosmic structures challenges our understanding of how galaxies and clusters form. If these seeds existed, they would have been critical players in setting up the framework for galaxy formation, a process that continues to unfold across billions of years. In some models, primordial black holes could be responsible for dark matter, a mysterious component making up about 85% of the universe's mass. This idea ties together two enigmatic phenomena, one from the early universe and another that remains unexplained in our current understanding of cosmic structure. The connection between these tiny entities and the vast distribution of galaxies is both profound and speculative. Primordial black holes, if they exist, would have been part of a fleeting era when quantum fluctuations could directly influence gravity's pull on matter. Their formation marks a unique moment in the universe's history, where the rules governing large-scale structure were set by events at subatomic scales. This interplay between the incredibly small and the impossibly vast is a testament to the complexity hidden within the cosmos, shaping the structures we observe today. Consider now how these tiny black holes might have influenced the formation of supermassive black holes found at the centers of galaxies. These larger black holes could grow from the accretion of gas and dust, but the presence of primordial black holes nearby would provide an alternative seeding mechanism. The gravitational influence of even a small primordial black hole could draw in additional matter, creating regions dense enough to form supermassive entities over time. The implications of this idea stretch far beyond mere cosmology. It touches on our fundamental understanding of how the universe evolved from its inception. If these tiny seeds were indeed responsible for some fraction of dark matter and galaxy formation, they would bridge a gap between quantum mechanics and astrophysics that has long puzzled scientists. The potential connection between subatomic physics and galactic-scale phenomena is both intriguing and humbling, reminding us just how interconnected the universe truly is. Primordial black holes represent an enigma wrapped in mystery, entities born at the very moment of creation that could play a crucial role in shaping the structure of our cosmos. Their existence would mean that the universe's early moments were far more dynamic than previously thought, with quantum processes directly influencing the large-scale architecture of space itself. This idea offers a window into the earliest epochs of cosmic history and challenges us to rethink what we know about how galaxies form and evolve over time. As we ponder these tiny black holes from such an ancient past, it's worth reflecting on their potential impact. If they existed in sufficient numbers, their gravitational influence could have sown the first seeds for the vast cosmic structures that define our universe today. This interplay between the microscopic and macroscopic scales underscores the intricate nature of the cosmos, a structure woven from the very fabric of time itself. Quantum entanglement presents a peculiar phenomenon in the universe, one that challenges our understanding of information's fate within a black hole. Imagine two particles entangled at opposite ends of space. When one particle is altered, its counterpart instantaneously responds, regardless of distance. This bizarre connection defies classical physics and suggests an intricate link between distant regions of spacetime. In this context, quantum entanglement could allow information encoded in particles falling into the black hole to reappear elsewhere through entanglement. When matter approaches a black hole's event horizon, it seems to vanish into the singularity. However, recent theoretical models propose that information might not be lost forever. Instead, it could be transformed and transmitted across vast distances via quantum entanglement. This process suggests a deeper unity within quantum mechanics and general relativity, hinting at how what appears to be lost is merely transformed into another form of existence. Consider the event horizon of a black hole with 1.4 solar masses. Its Schwarzschild radius is approximately 8 kilometers. Here, spacetime curvature becomes so extreme that not even light can escape. Yet, near this boundary, quantum effects might enable information encoded in particles falling into the black hole to be transmitted elsewhere through entanglement. This phenomenon implies a complex relationship between distant parts of the universe, offering clues about how nature preserves information. Researchers studying remnants of stellar explosions, known as supernovae, have observed patterns that suggest such connections. These observations indicate that particles emitted during these cosmic events might be entangled with those inside collapsing stars, potentially preserving some information despite the violent processes. This research offers insights into how quantum entanglement could play a role in the broader universe, challenging our conventional understanding of information loss. Quantum entanglement challenges traditional notions of locality and causality. While it remains a topic of intense debate among physicists, its implications are profound. Consider how this principle could apply to human-scale communication. If we could harness the principles of quantum entanglement, instantaneous information transfer might become possible. This thought experiment highlights the potential for revolutionary technological advancements inspired by cosmic phenomena. As we contemplate these paradoxes, it is worth noting that black holes themselves are not static entities, but dynamic objects that evolve over time. A small black hole grows faster than a large one due to accretion processes, and this growth can influence its entanglement properties. Understanding how information might escape from such evolving systems provides insights into the fundamental nature of spacetime itself, revealing a universe far more interconnected than previously imagined. This dynamic process suggests that black holes are not merely points of destruction, but also pivotal nodes in the cosmic web of quantum connections. Furthermore, these theories suggest that the universe might be far more interconnected than we can perceive directly. The idea that information from a black hole could reappear elsewhere challenges our conventional view of causality and locality. This paradoxical process hints at an underlying unity in nature, where distant points in space are not entirely disconnected, but subtly linked through quantum entanglement. As scientists continue to explore these concepts, they may uncover new ways to understand the universe's deepest mysteries, offering a glimpse into the profound interconnectedness of all things. At the edge of a black hole's event horizon, space-time stretches infinitely yet remains unmeasurable. Imagine an object approaching this boundary. It experiences time increasingly more slowly as it nears. Every second outside feels like an eternity for the object within this gravitational well. This phenomenon is known as gravitational time dilation. Consider how, from an external observer's viewpoint, a person near the event horizon appears to be frozen in time, their actions slowed to a halt. Yet, for that individual, time continues normally, though they are subjected to extreme tidal forces. The closer one gets to the boundary, the more pronounced these effects become. This paradox highlights the peculiar nature of relativity at such extremes. Temperature near this boundary is around 1 femtokelvin, making it one of the coldest places in the known universe. Despite this coldness, the event horizon marks the point where light itself cannot escape the black hole's grip. The energy required to break free exceeds the capacity of any photon here, creating an impenetrable barrier. This region acts as a cosmic prison for all matter and radiation that crosses it. Imagine standing at a precipice that separates two realities, one in which time flows normally and another where it halts abruptly. For someone observing from afar, you would appear frozen on this brink forever, your existence stretched infinitely thin by gravity's immense force. This boundary marks the transition point between the known universe and the unknown realm of singularity within. At the event horizon, spacetime undergoes a peculiar transformation known as frame dragging. This effect drags nearby spacetime along with it as it spins, creating an environment where even light follows twisted paths. The faster the black hole rotates, the more pronounced this dragging becomes. For example, near a rapidly spinning black hole, the path of photons can be significantly altered, causing them to loop and spiral in complex patterns. Within this region, objects closer to the event horizon experience increasingly stronger tidal forces. These differences in gravitational pull stretch matter into long strings, a process known as spaghettification. For someone approaching such a boundary, their body would be stretched and squeezed in unimaginable ways. Yet time would still seem to slow down for them, creating an eerie disconnection between reality and perception. This extreme stretching of space-time near the event horizon is so powerful that it can tear apart even atoms into individual particles. The age-old question persists: could these regions serve as gateways to other parts of the universe, or perhaps different dimensions? While we have no definitive answers, the physics at play here challenge our understanding of reality. The mathematics describing black holes suggest possibilities beyond what is observable in our current understanding. Perhaps within this infinite stretching lies a key to unlocking mysteries of the cosmos. As you rest, consider the vastness of space and the peculiarities it holds. These regions, where gravity reigns supreme, present both challenges and opportunities for exploration and discovery. The event horizon remains one of the most intriguing frontiers in our quest to understand the universe. In a region of space where multiple black holes reside, time behaves in ways that challenge our understanding. Imagine two supermassive black holes, each with masses far exceeding those of entire galaxies, orbiting one another at incredible speeds. The gravitational dance they perform creates ripples in the fabric of space-time that can stretch and compress time itself. These temporal distortions are not uniform. Instead, they form what scientists call islands of altered time flow around each black hole. Within these islands, time does not pass linearly as we experience it on Earth. A single day could feel like an eternity or a fleeting moment, depending on the proximity to the event horizons. Consider how this phenomenon would affect an observer nearby. Their watch might show hours passing, while only seconds have elapsed from our perspective. This warping of time is not just theoretical, it's a consequence of Einstein's theory of general relativity. The closer you get to a black hole, the slower your experience of time becomes relative to someone far away. Imagine being in such an island. Every heartbeat would synchronize with cosmic rhythms that are nearly imperceptible on Earth. Near a black hole with 10 solar masses, for example, an observer might perceive only minutes passing when hours have elapsed from our perspective. These islands of altered temporal flow extend outwards like bubbles in space-time, each influenced by the gravitational pull of its respective black hole. The boundaries between these regions are not sharp, but rather zones where time gradually slows down or speeds up depending on proximity. This phenomenon is akin to standing at the edge of a vast lake and watching the water ripple outward from a thrown stone. Interestingly, within these islands, distant stars may appear brighter as light bends toward Earth due to gravitational lensing. While these time-warped areas exist in theory, their practical observation remains a challenge for astronomers. Detecting such phenomena requires precise measurements over long periods that current technology struggles with. Nonetheless, scientists use indirect methods, like measuring gravitational waves, to infer the presence of multiple black holes and the effects they have on spacetime. For instance, when two black holes merge, the resulting collision sends out ripples in spacetime that can be detected by instruments like LIGO. The implications of these time-warped regions extend far beyond our understanding of gravity. They offer insights into the fundamental nature of reality itself. In a universe where time can be stretched or compressed, what does it mean for concepts like causality? Could events in one island influence those in another through this warping effect? These questions remain open as we continue to explore the mysterious realms around black holes. Theories suggest that within these regions, quantum entanglement might allow information to travel faster than light, challenging our classical understanding of physics and potentially leading to new discoveries about the universe's structure. The presence of multiple black holes can also create areas where time flows backward relative to distant observers. This phenomenon is not just a theoretical curiosity. It has practical implications for how we understand causality in extreme gravitational fields. Imagine an event occurring within one island, only to be observed as having happened before it did from another vantage point. Such paradoxes highlight the complexity of spacetime near black holes and challenge our conventional notions of time's arrow. Paragraph. Let us explore how studying black holes informs our understanding of gravity and its effects on Earth-based technologies like GPS satellite operations. Imagine an atomic clock floating in space above Earth's atmosphere. Its precision is such that it can measure time down to fractions of a second with extraordinary accuracy. This instrument is crucial for the operation of GPS satellites, which rely on precise timing signals to triangulate positions accurately across the globe. The stronger gravity near Earth slightly alters these clocks' ticking rates due to Einstein's theory of general relativity. These atomic clocks aboard satellites are so sensitive that they can measure time differences in microseconds, thousands of times smaller than an atomic diameter. This precision ensures that GPS systems function accurately within inches on Earth's surface. In regions closer to the planet, where gravity is stronger, time passes slightly slower compared to areas farther from the center. Remarkably, this minute effect has profound real-world applications, ensuring precise navigation and positioning. Now consider a black hole at the center of galaxy NGC 4261, where gravity is so intense that it affects not just time, but also light itself. The event horizon here marks the boundary from which no information can escape, not even photons. In this extreme gravitational field, objects orbiting the black hole experience significantly altered perceptions of time. If you could somehow stand at a safe distance near such an object, your biological clock would run faster compared to someone closer to its massive core, due to the difference in gravity's strength. Understanding these effects requires a deep dive into Einstein's equations of general relativity which describe how mass warps spacetime. The curvature of spacetime around Earth is subtle but measurable with precise instruments. This same theory predicts that black holes warp spacetime so dramatically that light itself cannot escape their gravitational pull. These predictions have been confirmed through observations and experiments, providing a foundation for technologies like GPS. The precision required by GPS systems involves atomic clocks accurate to within 1 nanosecond per day, ensuring the correct triangulation of positions across vast distances on Earth's surface. This level of accuracy is comparable to the sensitivity needed for detecting gravitational waves, ripples in spacetime caused by cosmic events. In 2015, these waves were first observed, confirming Einstein's predictions about how spacetime behaves under extreme conditions. The study of black holes reveals that these environments provide a natural laboratory for testing theories about gravity and its effects on time, offering insights into the structure of spacetime itself. Each new measurement brings us closer to unraveling the mysteries of spacetime. Technologies like atomic clocks aboard GPS satellites rely on our understanding of how gravity influences time. By observing how light behaves near an event horizon, scientists can confirm aspects of general relativity with unprecedented precision. These observations offer insights into spacetime's structure and its limits under extreme conditions, informing both theoretical physics and practical applications here on Earth. Understanding the intricate relationship between gravity and time around Earth is crucial for technologies we use daily. The Event Horizon Telescope project captured the first-ever image of a black hole shadow in 2019, providing visual evidence of these predictions. This observation offers insights into spacetime's structure and its limits under extreme conditions, further validating Einstein's theories. The same principles that govern time dilation around Earth also apply in deep space, guiding our understanding of black holes and their influence on surrounding spacetime. The accuracy required by modern atomic clocks is comparable to the sensitivity needed for detecting gravitational waves, ripples in spacetime caused by cosmic events. Each new measurement brings us closer to unraveling the mysteries of spacetime itself, from the smallest atomic scale to the grandest cosmic structures. As a supermassive black hole at the center of galaxy NGC 4261 begins its final stages of evaporation, it is estimated that this cosmic giant, with a mass of about 1 billion solar masses, will eventually shrink to near-zero dimensions. The process, driven by Hawking radiation, unfolds over incomprehensibly long timescales, longer than the age of the universe itself. Even the faintest particles of light carry away minuscule amounts of energy from its immense gravitational well. This slow evaporation is so gradual that it challenges our understanding of time and scale. At this stage, the black hole's event horizon is not a static boundary, but an evolving surface that gradually contracts. For an outside observer, it appears as though matter and energy are slowly being drawn into the ever-shrinking void. Inside, however, time behaves in ways beyond ordinary comprehension. The fabric of reality warps and twists as the black hole's mass diminishes. This phenomenon highlights how our perception of time can vary dramatically depending on proximity to such extreme gravitational fields. As the supermassive black hole nears its end, it releases a torrent of Hawking radiation, though this process is incredibly faint for such massive objects. The temperature at the event horizon remains extremely cold, around 1 femtokelvin. This radiation hints at quantum processes occurring in regions where gravity reaches its zenith. These processes suggest that even within these extreme environments, particles and antiparticles can briefly emerge near the boundary of absolute darkness. The final moments before complete evaporation involve the black hole's mass shrinking to such an extent that it may leave behind a Planck-scale remnant or perhaps nothing at all. Some theories propose quantum effects might imprint a trace of the black hole's history, while others suggest its total annihilation is possible. In either case, the universe will be left with only scattered particles as echoes of its former grandeur. These remnants, if they exist, could offer clues about the nature of space and time at scales where classical physics breaks down. Imagine an observer hovering just outside this event horizon as it contracts. Time for them would stretch to infinity, much like when we considered the perspective from the outside, the beginning of our journey. The boundary between existence and non-existence blurs, with matter on one side and the void on the other. This observer might witness the last flickers of radiation before the black hole fades entirely, leaving behind a quiet emptiness where once there was an object of unimaginable density. In the deep future, when remnants or nothingness are all that remain from supermassive black holes like NGC 4261s, these voids will influence their surrounding galaxies in subtle ways. The gravitational echoes of these objects could guide stellar orbits and distribution for billions upon billions of years, long after they have ceased to exist as we once knew them. Thus, even in absence, the profound impact of black holes endures. They are not just cosmic grav, but also architects of galactic structure and evolution over unimaginable timescales. At the event horizon, time stretches endlessly for those watching from afar, yet in a blink you pass through. As your journey through this cosmic dream begins to end, know that you are always welcome here. Thank you for sharing this moment with us tonight. If you enjoyed it, consider subscribing and leaving a like. Good night, and may the stars guide you gently back home.